All right, chapter 13 starts off and talks about properties of solutions. All right, chapter 13 is all about the properties of solutions. So here we're going to start off and look at exactly remembering what solutions are. So here it says solutions are homogeneous mixtures. Okay, your solvent is the dissolving medium, meaning it's the largest amount, usually that's water, and your solute is the thing being dissolved, it's the thing in smaller amount, usually the solid, okay, like salt or calcium chloride or whatever, okay. Now let's remember that solutions can be in any state though. We often like to think of a solution being salt dissolved in water. Well, you can also have, like you see in the table there to the right on your notes, a gas-gas solution, which would be like air. You can have a solid-solid solution, which is going to be an alloy, okay. You can have a liquid-liquid like alcohol and water. You can have solid and gas, solid and liquid. So there are other types of solutions. All it has to be is a homogeneous mixture. As long as you cannot tell one thing from the other, okay, that's going to be homogeneous. It'll be a solution, okay. Now we have the ability of a substance, okay, to dissolve. Depends on a couple of things, and there depends on two main things, okay. Depends on the type of intermolecular attraction and the natural tendency of the substance to spread. So one of those two things will help tell you a little bit about how well it actually dissolves. Okay, so now we're going to look at the effect of intermolecular forces. So let's remember here that there are different types of intermolecular forces. Okay, we've got 5. We have hydrogen bonding, we have a dipole-dipole, we have an ion dipole, a London dispersion, and then you've also got just normal ionic bonds. So these ones here are a covalent, okay, between two covalent molecules. This one was between an ionic and a covalent, and this is between two ionic. So those are the basic types of intermolecular forces we have going on there. Okay, so solutions form based on the strengths of the intermolecular forces. If you look at NaCl, that readily dissolves because the ion is very attracted to your polar water and it breaks apart the salt. And so let's look at an example of that. So we have NaCl salt added to water, H2O. Water is my solvent, which means that it dissolves it. Okay, your negative sides of your water are attracted to your positive Na. The positive sides of the water, which are the hydrogen, are attracted to your negative Cl. Okay, this causes then the waters to surround each positive and each negative. And we call that a hydration shell, or just hydration, or solvation. And it prevents then the Na and the Cl from recombining into their ionic bond. And your salt then has what we call dissolved. Okay, so that's kind of what you have there in that picture on your notes. Okay, where the Na is a solid on the left. It's been slowly being torn apart by the waters that are then forming bonds to it. And then over there on the right, you see the Na plus and the Cl minus that are drawn out just like they were in that video. So just like you've got here, which is the picture you have, okay, the Na and the Cl are getting kind of torn apart by the very polar water. And again, we call that either solvation or hydration. Okay, so let's look at some energy changes that are associated with the solution formation. Okay, there are 3 steps to determining the overall energy of a solution. We have the separation of your solute, which would be the Na and Cl in our last example, so how much heat or energy it takes to pull that apart. We have the separation of your solvent, because that's got to be separated then to attach on to the solute. And then we've got the formation of the solute solvent. Okay, so we've got those 3 different kinds of energy to figure out exactly kind of whether the solution is endothermic or exothermic and whether you'll actually get a solution at all. And so the enthalpy of a solution, if it is positive, then it's endothermic. If it is negative, that is exothermic. And if we add them all up, the 1, 2, and 3, we're going to get the overall heat or enthalpy for our solution. So how much it takes to break the solute and then break the solvent, and then how much energy we get back when we put the two together. Okay, when you break an intermolecular force, which is always H1 and H2, those are always positive. Okay, and when we form an intermolecular force, that's H3, that is always negative. And that forming intermolecular forces is actually on the top of the next page. So don't try and write that all in one little spot there. Okay, and again, we have that drawn out there with those beakers in your notes. You're breaking it in one, you're breaking the other in two, you're putting them together in three. Okay, so how do I predict if a solution is going to form? Well, if your delta H, so that D is actually one of those triangles. Okay, if my delta H for my solution is negative, then it's going to form. All right. Ionic bonds do not dissolve in nonpolar liquids because my London dispersion or the nonpolars are not very strong. So they're not strong enough to then break the ionic bonds and pull it apart. So this gets us to the like dissolves in like. Okay, you have to have a strong enough solvent that can pull apart my solute. If your solvent is too weak, it's not going to pull it apart. So a London dispersion, a weak force, cannot pull apart a strong ionic or a strong polar. That's why like in like. Polar dissolves in polar, nonpolar dissolves in nonpolar, because nonpolar is strong enough to rip apart a nonpolar. That's kind of what we're going to look at a lot here. And you have that example there on the right side. Okay, if you have a net exothermic, okay, or a net endothermic, and they're showing you there the examples with the H1 and H2 and H3. Okay, so let's look at then solution formation, spontaneity, and disorder. Okay, spontaneity is that two solutions mix without any input from the outside system. They just spontaneously happen. It just happens. Okay, you don't have to put anything in to get it to go. It just goes. All right, that's spontaneity. Okay, now there are two factors that go along with figuring out if something is spontaneous or not. Okay, that's my energy, whether it's positive or negative, and then my tendency of a substance to spread out and mix. And we're going to look a lot more closely here at exactly what these factors are, okay, and what this tendency to spread out and mix is going to be. It has to kind of go along with, like, if you put food coloring in water, the food coloring is just going to spread out. Okay, that's the tendency of it just to want to mix. Okay, a little bit more about spontaneity. If the energy of a system decreases, the process is spontaneous. That's exothermic and that's negative. So my energy of my system goes down, becomes more stable. My processes are just going to happen. Ice just melts. Okay, allowing the system to become more random or dispersed. Okay, that's the randomness increases. That's being spontaneous as well. Okay, so again, those two kind of factors, I kind of just explained them twice. All right, and you've got a picture there of a CCl4 and C6H14, and they're separated, and then in B, they're mixed. That's a spontaneous. Things just like to mix. We're not going to say separated there if there is not a barrier there anymore. So let's talk about that kind of increasing in randomness here. And that is what we call entropy. That is the amount of randomness or disorder of a system. So like I said here, I have the CCl4 and the C6H14 initially apart. I open up that barrier in the middle and now they are all spread. That is entropy, or that things want to be more disordered. Okay, will a solution form based on attractions? Okay, solutions will always form because things like to spread out and increase their randomness unless your solute, or solvent are too strong compared to what they are together. So that's the whole thing with like and like. Okay, a weak force is not going to break apart a strong force. So unless they are too different, okay, a solution will always form. Things like to be more random. Okay. Now we're going to look at chemical reactions, okay, and chemical versus physical processes and how solutions are being formed here. If it's a chemical, let's remember, then that means my substances have changed and cannot change back. So I've got an example here of nickel. That's an N. It looks kind of like a W. Okay. Nickel and hydrochloric acid is going to react to make nickel chloride and hydrogen. Now these things are in a solution. So if I have a solid, okay, S, acids are always aqueous. This is going to be aqueous, and this is going to be gas. So I have a solution here with these aqueous things. but it's not actually a physical process. You're not just making a solution that is the same thing as what you had to begin with, which would be a physical one down here at the bottom. Your substance isn't changed in the process and can get changed back. So I have a solution of salt and water, and I make a salt water solution, but if I just take the water out, evaporate the water out, I still have salt. So you can have solutions that are both a chemical process and a physical process. Okay, so let's look at an example here. It says in the process illustrated below, the water vapor reacts with excess solid sodium sulfate to form a hydrogen form of a salt. And we have Na2SO4 and my waters around it. Remember, that's a hydrate. This 10 waters means I have 10 waters around my Na2SO4. We talked about that last year. Okay. If essentially all of my water vapor in the closed container is consumed in the reaction, we consider our system to consist of initially of just the water and the sodium sulfate separate. Now, does your system become more ordered or less ordered, and does the entropy increase? Well, I've got the answer here. It's more ordered because I'm taking these little waters and I'm attaching them to a solid. So my waters now are no longer all around it. They're attached to it. They're stuck in a spot. So they're way more ordered in a solid than they are apart as a gas. Okay, gases are very random and have very high entropies. So my entropy is going down.